All right, we get to actually start talking about what is chemistry in this podcast. And don't let those page numbers get you down. It's really just a little bit of page 4 and 6 and all of page 5, but we're going to be drawing some simple circles in those big squares. It's going to take up a lot of space, but it's really not that much work. So let's get started with talking about, well, what is chemistry, this class that I've been enrolled in. In chemistry, we study matter and the changes that it undergoes. So that kind of leads directly into, well, what is matter? And matter is anything that has mass and takes up space. So anything that you can measure its mass or its weight and its volume, that's the takes up space part, then that means that that substance is matter. And so we're going to be studying it and how it acts and how its atoms act and react and how the subatomic particles act and react with each other. And we're going to be looking at every single different type of matter at all different levels and how it changes. So once again, we kind of have to start talking about, well, is this matter, and being able to have that discussion. So in class, we'll talk about this, but I want you to start thinking about, is air matter? Can you prove it? How would we need to prove that? And then on the other hand, is there anything that isn't matter? Anything that doesn't have mass and weight or doesn't take up space? So think on those questions, and we will talk about that in class a little bit. So I used the words mass and weight on that last slide when we were talking about mass, and really they're very similar. And for a chemist, I'll explain why we're mostly caring about the mass, but if you say weight, it's not the biggest idea. You're not just completely wrong, but they are different. Mass physically measures the amount of matter in an object. So if I tell you that there's an average of 100 trillion atoms in every human cell, that's a measure of its mass. That's telling us exactly how much stuff is in an object. And then weight, on the other hand, is the gravitational force exerted on an object. So I have a very physicsy equation here that you do not need to know, but that's the equation that we use to calculate weight. And the first part of it is mass. So we got to have mass as part of weight, but then it's multiplied by the gravitational constant of whatever planetary body you are on. So here on Earth, that's 9.8. If we go someplace like Mercury, where that gravitational constant is lower, even if I have every single atom still in my body and the mass of me is the same, my weight would be lighter. If I go to someplace with a higher gravitational constant, I would feel heavier. Even though I hadn't gained any mass, I will have felt like I gained weight. So it's asking you to compare those two, and you can absolutely use your own words to describe the difference between mass and weight. But really, if we go back to those definitions, where mass is the amount of matter we have, if we want to change mass, we've got to change ourself and the amount of matter that's inside us. So like Bart Simpson is adding a little bit of mass to his body, or that lab safety sign shows someone removing some mass from their body, their mass is different. But to change your weight, you could just change gravity. You don't have to change yourself, but you could lose weight just by going someplace where there is a lower gravitational constant. Now make sure you got that there before we move on to page 5 at the top. We're going to start by defining physical properties, which are pretty simple. It's just describing what you see, what something is or what it appears to be. Now we're actually going to take a quick little foray down to the bottom of the page because I really do want to define these words together. At the bottom of page 5, you see the word chemical property, and this might just help you understand the difference between the two. A chemical property describes how a substance can change. That's generally going to involve changing into a new substance. And what's really important is that we can only measure or observe these properties by changing the substance's structure. So if we think about some examples for them, reactivity. I cannot tell if sodium reacts with water until I actually put sodium in the water, and then I know sodium is highly reactive in water. That's a chemical property. I can't tell just by looking at the sodium, oh, that's going to react with water. Same kind of thing with flammability. That's really kind of just a special type of reactivity where something is very reactive and to flames and fire. Toxicity, you can't tell if something is poisonous until you actually expose the cells to that substance and see how they act and interact there, as well as acidity. So those are our chemical properties, and they tend to be a little bit kind of more involved in the measuring process there because you got to do a lot of work to actually observe those. So going back to our physical property, you can already see some examples of physical properties here. I can just put a substance on a scale and that measures its mass. At a more simple level, color is a physical property. It's just a color. I can see that without having to do anything or change anything about that substance. Volume is a physical property. We can look at that in a beaker. We can tell how much space it takes up without having to change that substance. So let's talk about a couple different types of physical properties. These words that we skipped over here, intensive and extensive. So intensive properties are physical properties that do not depend on how much matter is present in order to measure them and observe them. Extensive properties, on the other hand, change when we change the amount of matter present. So in order to help you understand this difference, and we'll spend a little bit of time in class talking about this and making sure you understand it a little bit more, think about me with a beaker of water. If we talk about, or we could even Google, the boiling point of water, kind of doing these first two examples to help you see the differences here. Google and everywhere else will tell you that the boiling point of water is 100 degrees Celsius. This volume of water, I'm not exactly sure what these tick marks represent, but it looks like we're just about halfway between the third and the fourth tick marks. So we've got about 3.5 ticks of water, whatever volume that happens to be. Now imagine that I have another beaker of water and I come and I pour that water into this beaker so that we have more water in that beaker. This is all now filled up. So now that I've added more water, what's the new boiling point of water? Well, Google didn't say it depended. It just says 100 degrees Celsius. It doesn't depend on how much water we have. The boiling point of water, whether I have 3.5 ticks of water or 5 or 10 gallons of water, is always going to be that same 100 degrees Celsius. And because of that, because it does not depend on the amount of matter, boiling point is intensive. Volume, on the other hand, if I add more water to my beaker, I now have more tick marks. This looks like I'm all the way up to 4, 5, 6, 7 ticks. So my volume has doubled just because I added more water in there, and that's probably pretty obvious to you. Of course, more water means more volume, but that is the definition of an extensive property, where the property changes when the amount of matter present changes. So go ahead and look at these next 4 examples here and just maybe put an I or an E next to them based on whether you think that property would change when we change the amount of matter. And visualize this beaker of water. Think, oh, okay, with more water, would the mass have changed? Would the length have changed? The density, the boiling point? If you have this simple example in your head and think, okay, more water, does this change? You can always get back to these definitions and the answer pretty easily. So let's move on to some more general ideas, things that you're probably aware of. The 3 common states of matter are solids, liquids, and gases. And the most fundamental definition is that solids have a definite, meaning not changeable, shape, and a definite, not changing volume. Their molecules cannot move around as much as in our other 2 states of matter. The molecules are just sitting in the same place, stuck between the same molecules and atoms that they always have been, and the only energy, motion that they have is to vibrate in that structure. Liquids, on the other hand, can change their shape. We call that indefinite shape, but they do still have definite volume. Think of water. We can measure the volume of water. It's not just going to expand and overflow the beaker as soon as we pour it in. That's because the molecules can flow. That allows that shape to change, so it goes from being water bottle shaped in your water bottle to beaker shaped in the beaker, or floor shaped if you pour it on the floor. The molecules can move and flow, but there's still some attraction between those molecules, so they can't escape and just fill up whatever container they're in. And as you're probably aware, gases can change their shape and their volume, so they have indefinite shape and indefinite volume. And that's because the molecules are not attracted to each other at all. They can just go anywhere, do whatever, and there's nothing holding them down. So you probably knew that already. We are going to be talking about one other state of matter in the future, and that's aqueous. So if you make a little note in a margin, or if you have space down here below, you can. And aqueous just means dissolved in water. This isn't a liquid. It's something that's made to act like a liquid because water is liquidy, but we dissolve it in water like salt water. That's a aqueous solution. We'll talk about the word solution later on, but that is technically another state of matter, just a little less common. And we will be using some abbreviations for these, so especially in some of your answers and shorthand, you can use SLG and then AQ for aqueous. And the next thing we're going to do is draw some particles in these boxes to model what these different states of matter look like at the molecular level. And I'm going to be drawing these little blue circles to fill in these boxes to show these differences. So just make sure that you're kind of using similarly sized, neat circles in these boxes. And if we remember, solids are definite shape, close together, little bit like barely vibrating, and not really moving around in order to change their shape or volume. So I drew all of my circles at the bottom, and they're all very closely packed and regularly arranged in that kind of rows. Liquids, even with the same number of particles, they're going to be a little bit farther apart. They're going to have some random distances between them, and they will still mostly be at the bottom. They can't expand and take up whatever shape the container is and volume that container is, but they do still get to flow and move some. And then gases, I have a few less particles in here, but I just wanted to really show that they have greater distances between them, and they can go and fill up the entire space that you put them in. They're not just going to sink to the bottom. They're going to expand and fill whatever container you put them in. So now moving on to how matter is going to change. Starting the top of page 6. Remember, we did write down that definition for chemical property already. So these are physical and chemical changes, which are pretty similar to the properties. This is just the action of changing those physical properties. So physical changes change that outer appearance, the way it looks. It does not change the composition and what that substance is made of. Chemical changes, on the other hand, involve changing that substance into a new substance. So it's an entirely new chemical, not the old chemical at all. So changes the way it looks, changes the way it is. Now, off to the side, I do need you to write down these indicators of a chemical change. You do need to know these very, very well. And once again, we'll talk about them and explore them a little bit more in class. The first one, the first sign that a chemical change might happen is bubbles. You mix baking soda and vinegar together, a solid and a liquid, and then all of a sudden you are forming a gas. That's a sign that that is a new substance that has been made. It's not a solid or a liquid, so it has to be something completely new. I'm not talking about like blowing bubbles in your milk or your water. You're making bubbles there, sure, but the air, the gas, was already in your mouth, so that's not creating a new substance. So with this, as with all of these other indicators we're going to talk about, make sure that it's a surprise gas, surprise bubbles, not just the same air just moved around. The second example is a solid precipitate being formed. Once again, this isn't just making a solid from other solids or something that was already there. Imagine taking two completely clear, transparent liquids that just look like water. You mix them together, and then all of a sudden you've got like blue chunky stuff falling out, or like yellow chunky, like what happened there? That's a solid that was made from some liquids. That must be a new substance. It's definitely not the old substances. The next one is either heat or light released, and these do still count just as one indicator because both of those are signs of an energy change. So that's really what we're looking for, is that energy change between the stuff we're starting with and then what we're ending with. But the way that we would actually indicate or see that energy change happening is we would feel that heat, or we would see that light being released, and that shows us that there is some energy coming off. And then, of course, a color change. And if something starts off blue and you pour some clear liquid into it and it turns red, that's surprising. You wouldn't expect blue plus clear to make red. If I put blue stuff into clear stuff and it turned a nice light bluish color, that's not a chemical color change. Blue and clear make blue. That's like basic elementary color combinations, or blue and white make light blue. That's normal, just mixing things. The chemical change is going to happen when you have that surprise color change, that surprise bubbles, surprise solid, surprise heat or light. So those are really important to understand, so we'll spend more time on them in class. But that's what we're looking for when we see these examples that we need to classify. We need to ask ourselves, are we forming a new substance? Are any of those indicators happening when I break a pencil? Well, no, there's no bubbles. There's no surprise solid. All the solid stuff I've got was still there before I broke the pencil. It's just in two pieces now. There's no heat or light released, and there's no color change other than seeing the inside color of the wood that might have been hidden before. The wood was still that color, I just didn't see it. So breaking a pencil, I don't see any of those indicators. That means it is a physical change. Frying an egg, it does bubble. I do have that liquidy egg suddenly just turn solid. And you wouldn't think that heating something up, it would turn solid normally. Heating up ice, it turns to a liquid. So we're creating a surprise solid. The heat light isn't happening there because the heat for frying an egg is coming from the stove. That's not surprise heat. And if I put something on a stove and it gets hot, I'm not like, oh my gosh, it got hot on the stove. That's what stoves are supposed to do. That shouldn't be a surprise. But we did see bubbles, we did see solid, and we probably also see the color change from clear to white, from yellow to kind of off yellow. So this is a chemical change. We don't need all of those indicators. Any one would be enough. But the more you have, the more evidence you have that it is a chemical change. And then E shouldn't even be a debate. It says leaves turning color. The leaves are changing color, and no one's going out and painting them a different color. So that is a surprise color change, and that is definitely a chemical change. I'm going to leave these other three for you to try out and give your best shot at, and then we'll go over them in class and make sure we're all on the same page. And then, last but not least, define the law of conservation of mass. Well, conserving mass, just like if we want to conserve elements or conserve water, means saving it. We're not destroying it. It's not going anywhere. So the law of conservation of mass says that in all of the changes that we're going to be studying, no mass is going to be created or destroyed in these chemical reactions. It's all going to be there at the beginning. It's all going to be there at the end. It just might take a different form. Now, there's going to be lots of examples, and if you have some simpler ones you want to write down, that's great. But especially for chemistry, chemical reactions are going to be our best example of conservation of mass. And we're going to be balancing chemical reactions with these numbers, the 2, 2, and the 1 that I added in there, in order to keep them balanced, in order to make sure that the number of atoms of each type is the same both before and after the reaction, before and after the arrow. So we'll get a lot more into those details, but none of those atoms are going anywhere. They're all still there. They're just a little more separate than they were before the reaction. And if I were to do a lab with this reaction, and I knew I started with 216 grams of that HGO stuff, and then afterwards I knew and measured that I made 200 grams of that Hg, then I could figure out how much oxygen I was made, because this has to add up to 216 grams. It's got to be the same mass I started with, so that means that the oxygen must have been about 16 grams. So that's the idea that we're trying to hit home here, is just that this arrow, which represents our dividing line when our reaction happens, that everything we had over here is going to be equal to the stuff we have over there in every way. Looks a little different, acts a little different. So thanks for sticking with us on this podcast. This is officially the end of the slideshow.